The other day we talked about the noble gas electron configuration, and one of the trends that we talked about was the same ending configuration is going to exist on the periodic table. Again, with that S, P, D, and F block. Again, if they were within a certain column, again, they might all end in P2. They might all end in D3, or they might all end in an S1. But the only thing that was going to be different was going to be the energy level that they were in. There were four more trends that we need to talk about on the periodic table. Those four trends are going to be atomic radius, ionic radius, ionization energy, and electronegativity. Atomic radius. Atomic radius is just going to be half the distance between adjacent nuclei of a crystal or a like atom. And what we mean by that is, again, we cannot measure a single atom. And again, the reason why we cannot measure a single atom is if you remember that 90% rule, again, the electrons do not have a defined outer shell. And again, 90% of the time they are here. So what they do is they measure from the nucleus of one atom to an adjacent nuclei of the next atom. The trend, within a period, the atomic radius is going to decrease. And again, the reason why it's going to decrease is because electrons are being added to that same energy level. If we are in period number 2, starting with lithium, again, it's going to be a 2s1. We get over to carbon, again, it's going to be a 2s2, 2p2. Unlike lithium, that's going to have one valence electron, carbon's going to end up having 4 valence electrons. You get over to fluorine, which will actually have a 2s2 and a 2p5. Again, the thing that you're going to notice is, again, lithium has 1 and fluorine's going to end up having 7 valence electrons. Those electrons were added to the same energy level. Anytime you add electrons to that same energy level, what you're going to notice is it's giving you an increased atomic charge. And that increased atomic charge is going to end up producing a greater attraction within that energy level. And because of that greater attraction, you're going to notice that the atomic radius is going to decrease. Within a group, the atomic radius is going to increase. Again, the reason why it's going to increase is within a group you're getting to those higher energy levels. Yes, they might all end in an S2, but we're going from a 2s2. The next one's going to be a 3s2. The next one's going to be a 4s2. And so forth. You're getting to those higher energy levels. But as you get to those higher energy levels, you're actually adding more and more electrons to those inner energy levels. And the thing is, those outer electrons are being shielded from the nucleus. And because you're being shielded from the nucleus, you're going to notice that the atomic radius is going to increase as you go down a group. So within a period left to right, atomic radius is going to decrease. And as you go down a group, you're going to notice that that atomic radius is going to increase. If we look at ionic radius, again, the majority of the elements on the periodic table are not stable. The only ones that are stable are group 18, or your noble gases. In order to become stable, an atom needs 8 valence electrons to obey that octet rule. Atoms can either gain or lose electrons to become stable. And when they gain or lose electrons to become stable, that's going to be an ion, which is just going to be any atom that has gained or lost electrons to become stable. The thing is, atoms are always going to take the shortest route to 8 valence electrons. So again, if you have 3 valence electrons, it's going to be a lot easier to lose those 3 than it is to gain 5. If you have 7 valence electrons, it's going to be a lot easier to gain that 1 than it is to lose all 7 of them. Any atom that loses electrons is going to end up having a positive charge, meaning that you're going to have more protons than electrons. And any atom that gains electrons is going to end up having a negative charge, which just means that you have more electrons than you do protons. Now, the one thing that I want to tell you is, because we have protons and protons are in the nucleus, basically what we're saying is electrons, because they are moving, what they're trying to do is they're actually trying to leave or pull away from the nucleus. And your protons, again, what they are doing is they're trying to pull those electrons towards the nucleus of that atom. As you move across a period, metals are going to decrease in ionic radius. Again, when you get to your first nonmetal, then what's going to happen is you are going to notice that there's a huge increase in size because we're switching from something that wants to lose electrons to something that wants to gain electrons. And what you're going to notice is most of your metals, because again they have few valence electrons, they are going to want to lose those electrons and develop that positive charge. Nonmetals, they generally have those 5 or more valence electrons, and what they're going to do is they're going to try and get or gain electrons. So again, as you go across the periods, metals are going to decrease in size. And then all of a sudden, when you get to that first nonmetal that wants to gain those electrons, you're going to experience a huge increase, and then all of a sudden that size is going to decrease. The example that I have up here, it says as you go across period 3, it says sodium is going to have a +1 charge. It just means that you have one more proton pulling on those electrons. When you go to magnesium, now all of a sudden we have 2 more protons than electrons. And when you get to aluminum, it's basically like saying we have 3 more protons than we do electrons. And the thing is, a +3 charge is going to be able to pull on those electrons more than something that has a +1 charge. Just think of tug of war, okay? If you have 2 teams equal in size, okay, protons and electrons are equal, again, basically you'll be at a stalemate. But if all of a sudden I add one more person to a side, you're going to find out that they have more pull, so they can pull them over easier. Now all of a sudden magnesium's +2. Put 2 more people on one side. Again, they're going to be able to pull on those electrons more. And all of a sudden aluminum, now you have +3. Okay? You have 3 more people playing tug of war on one side. And what they're able to do is they're able to pull that team over sooner than something that only has a +1. Now, again, each one will get smaller because, again, as it says up there, there are more protons pulling those fewer electrons towards that nucleus. But the minute that you get to phosphorus, you're going to have a 3- charge. And again, what that 3- charge now says is that we now have 3 extra electrons, 3 more electrons than we do protons. And again, you're going to experience that big jump because remember what I said earlier. Electrons, because they're moving, they're trying to get away from that nucleus. So we have 3 extra things trying to get away from the nucleus, and that's why we experience that bigger jump. All of a sudden you go to sulfur, -2. Now you only have 2 electrons trying to get away, so it can't get away as much. And then all of a sudden you have chlorine, which is a -1 charge, which again, it's still trying to get away, but the thing is, it cannot increase its size as much as a -3. So what you're going to notice as you go across a group is the metals, again, +1, +2, +3, again, you're going to get smaller. And then the minute you get to that first non-metal that has a negative charge, you're going to have a huge jump in size. And then all of a sudden that size is going to decrease. So it says as you go down a group, all of them have that same charge. Okay, all of them are going to have a +1 charge, or all of them are going to have a -3 charge. What will happen is that ionic radius is going to increase again because of shielding. Yes, you have your valence electrons, but because of all of those inner electrons as you go down a group, those electrons are being placed further from the nucleus, and again, the nucleus can't pull on them as much. So as you go down a group, ionic radius is going to end up increasing. Ionization energy. Ionization energy is just the energy that is required to remove an electron from a gaseous atom. Again, all atoms, they necessarily don't want to. I mean, again, they want to have that same number of protons and electrons. But if we have to remove electrons, you're going to find out that it's going to be harder on some elements to remove them, and it's going to be easier on other elements to remove them. Metals, they want to lose electrons because, again, they generally have 3 or fewer valence electrons. The shortest route to 8 is going to be losing those electrons. So if metals want to lose electrons already, they're going to have a low ionization energy. It's not going to take very much energy to remove an electron from them. Now, nonmetals, on the other hand, they're going to want to gain those electrons. They don't want to lose them because if they lose them, they're getting further from being stable. So because they want to gain them and do not want to lose them, nonmetals are going to end up having a higher ionization energy. Again, when you look at a periodic table, you're going to notice that the metals are on the left, nonmetals are on the right. So when you go across a period, what is happening is you are switching from your metals over to your nonmetals. So the period trend for ionization energy is going to be, as you move across a period going from left to right, ionization energy is going to increase. And it's increasing because you are changing from a metal to a nonmetal in elements. The group trend in ionization energy is going to be, again, ionization energy is going to decrease as you go down a group. Again, I always keep bringing it up, this word shielding. Shielding is going to be one of those magic words that we're going to be talking about in this section. But something that's further from the nucleus can't pull on as well. And if the nucleus can't pull on it as well, it's easier to pluck that electron away from that atom. So again, as you go down a group, ionization energy is going to decrease because of shielding. That nucleus cannot hold on to those outer electrons as easy. When we go ahead and talk about compounds, because again, electrons are going to gain and lose electrons and form those chemical bonds and form those compounds to become stable. Electronegativity is the relative wanting or the relative attraction of the electrons to an atom when it is chemically bonded to another atom. Again, I've got two atoms there, or I've got two elements. Both of them are going to be technically pulling on the electrons because of the nucleus. But again, one atom is going to have a stronger pull than another, and that stronger pull is going to be called electronegativity, or that attraction, or trying to get those electrons to yourself. Again, metals want to lose their electrons, so they're going to have low electronegativities. Nonmetals on the right of the periodic table, they're going to want to gain those electrons, so they are going to have a high electronegativity. So that period trend is going to be, as you go from left to right across the periodic table, you're going to notice that electronegativity is going to increase. Because again, we are transitioning from metals to nonmetals. We're transitioning from something that wants to lose their electrons to something that actually wants to gain electrons. And group trend, as you go down, again, those electrons, those outer electrons are further from the nucleus. So as you go down a group, that nucleus cannot grab those electrons as easy. It cannot pull on those electrons as easy. So electronegativity is going to decrease as you go down a group.